We write code in a language that looks like English. Whether it's JavaScript, Fortran, or assembly language, that code is an abstraction on top of layers of intermediate languages, binary, transistors, and physics. 100 years ago, this would have seemed like magic. Most of us know about Alan Turing, who described the vision of a multipurpose computer with the concept of the Turing machine. Less well known is the scientist Claude Shannon, who laid the groundwork of information theory. With information theory, we can compress data and communicate it efficiently across channels. Soni and Rob Goodman are the authors of A Mind at Play, a biography of Claude Shannon. Claude's unique insights about information were made possible by his willingness to involve himself in lots of different areas: science, art, juggling, warfare, many more. This interview gives insights for how we can think of new ideas by synthesizing disparate subjects. There are 600 episodes of Software Engineering Daily, and it can be hard to find the shows that will interest you. If you have an iPhone and you listen to a lot of Software Engineering Daily, check out the Software Engineering Daily mobile app in the iOS App Store. Every episode can be accessed through the app, and we give you recommendations based on the ones that you have already heard. If you have suggestions for things you would like to see in the Software Engineering Daily app, please let me know. Send me an email, jeff@softwareengineeringdaily.com, or you can hop in our Slack channel and talk to the creators of the Software Engineering Daily mobile app, Keith and Craig Holliday. And with that, let's get on to this episode. To build the kinds of things developers want to build today, they need better tools, super tools, like a database that'll grow as your business grows and is easy to manage. That's why Amazon Web Services built Amazon Aurora, a relational database engine that's compatible with MySQL or PostgreSQL, and provides up to 5 times the performance of standard MySQL on the same hardware. Amazon Aurora from AWS can scale up to millions of transactions per minute, automatically grow your storage up to 64 terabytes if need be, and replicate 6 copies of your data to 3 different availability zones. Amazon Aurora tolerates failures and even automatically fixes them and continually backs up your data to Amazon S3. And Amazon RDS fully manages it all, so you don't have to. If you're already using Amazon RDS for MySQL, you can migrate to Amazon Aurora with just a few clicks. So what you're getting here is up to 5 times better performance than MySQL with the security, availability, and reliability of a commercial database, all at 1/10 of the cost. No upfront charges, no commitments, and you only pay for what you use. Check out aurora.aws and start imagining what you can build with Amazon Aurora from AWS. That's aurora.aws, aurora.aws. Soni and Rob Goodman are the authors of A Mind at Play, a biography of Claude Shannon. Guys, welcome to Software Engineering Daily.
Thanks so much for having us.
Thank you for having us.
So we're talking about Claude Shannon and information theory because he was essentially the father of information theory. Why was Claude Shannon important?
Claude Shannon is important because in a lot of ways he's a founder of our era. He's someone that makes possible so many of the digital technologies that we take for granted every day. He's someone who comes up with the intellectual architecture behind digital computing. In a master's thesis he writes in 1937, which a lot of people consider the most important master's thesis ever written, when he's just 21, by the way. And later on, he goes to found the field of information theory, which allows us to do such things as quantify the amount of information in any sort of message in bits, and allows us to encode those messages in digital bits and make it possible to compress them and then send them with perfect accuracy. I don't think it's an exaggeration to say that without this architecture that Claude Shannon laid down in the 30s and 40s, we wouldn't have any of the digital technology we rely on today. Claude Shannon is that important for establishing some of the intellectual conditions for the modern world.
Mm-hmm. I'd like to make our way towards the circumstances in which Claude was able to have these fundamental insights about information theory. And I think a lot of it has to do with who Claude Shannon was as a person kind of outside his engineering and computer science time. And I think you hearken at this with the title, which is A Mind at Play. Explain that title. Like, give us some characterization for who Claude Shannon was.
Well, I think this is one of the things that makes him such an extraordinary figure, is that he's not setting out to inaugurate the computing revolution or to create a digital world. He is pursuing problems that interest him. He's just basically following his curiosity. And at each stage in his life, what looks like work to other people is play to him. And it's interesting because he's not just this incredible theoretical mathematician. He's also somebody who becomes a juggler. He's actually pretty proficient at juggling. He rides unicycles. He plays chess. He builds one of the first wearable computers to go and try to beat the roulette tables in Las Vegas. So he's somebody who, with every project, with every paper, it's in a spirit of play. There's a real lightness about him and his work. He's not the kind of tortured genius that we've come to expect and maybe even require. And so there's something about that really spoke to us. And then we just figured the title was such a perfect way to capture that. And it was probably the most important thing about his life, is that each of these experiments, each of these innovations, each of these incredible papers, it's all done in that same spirit.
How did his early life shape who he became as a scientist?
Well, in a couple of ways. I mean, some of the obvious ways are that he was just born into a smart mathematical family. That's especially the case for his sister Catherine, who he said was the academic star of the family, who sort of got him interested in math really through a sibling rivalry. He said that she was always better at math than he was, and he wanted to catch up. But at the same time, a lot of his passions for things like tinkering and for things like code started in his early days. So Claude Shannon grows up in the very small town, just 2,000 or 3,000 people, of Gaylord, Michigan, which is in sort of the north center of Michigan. And he has a pretty rural, small-town childhood. But what he fills all that time with is stuff like building a barbed wire telegraph system that allows him to send messages back and forth between his house and his friend's house, and building a barn elevator so that they can ride it to the second floor of his friend's barn, and doing things like competing in the Boy Scouts wigwag signaling contest, which is all about imitating Morse code with flags that you hold. At the same time, Shannon really develops, even in these earlier years, a love of all things having to do with codes and code breaking. He said that growing up, one of his favorite stories was Edgar Allan Poe's The Gold Bug, and he also mentioned in another interview some of the Sherlock Holmes stories. And what these stories have in common is they have great digressions on how to break codes, whether they're criminals' codes or whether they're buried treasure codes from pirates. And he said his sister Catherine always gave him codes and math puzzles to play with, too. So anyway, this is someone who grows up whose intellectual interests really date back to the very earliest information we have about him, which isn't to say that he was sort of marked as a genius right away, and he was a good student, he got A's and B's. No one really singled him out as someone who's going to go on to be a world changer, but he was someone who was letting all these interests incubate and take root. And the neat thing about his subsequent career is that he would really just pursue the same sorts of interests, just in at increasingly high levels of abstraction. But you could say for Claude Shannon, not really increasingly high levels of fun, because he always had fun with it.
Claude Shannon studied both electrical engineering and math. What were the bridges that he was able to draw between these fields?
Well, in a way, he spent his entire life drawing bridges between those fields. And, he just to make sure everybody knows, he didn't see this as some deliberate strategy to become, both a mathematician and an engineer. When he arrived at the University of Michigan, the engineering school had expanded, grown a lot. There was one particularly entrepreneurial dean who managed to both increase the funding available, the number of students who came through, the programs that were offered, and in a sort of amoeba-like way, engineering starts kind of running up against different parts, other academic programs within the University of Michigan. And one of the things that happens is there's a lot of courses that are in common between math and engineering. So Claude Shannon's able to pick up the dual degree without too much effort. And so it's not like he was, doing this punishing academic course load. There was a lot of overlap. But in his case, it paid huge dividends because he's one of a handful of people who is able to both think rigorously about practical things like the Bell Laboratories telephone network, and that's based on his engineering background. And then also think about mathematical logic and apply mathematical logic later. And one of his early and most famous connections between the two is this master's thesis he writes when he's all of 21 years old that connects logic with circuits, that connects math with engineering. And that thesis, some people regard it as basically the foundation for all modern computing. And he does it when he's 21. And there are a number of things that are baked into his life that allow him to do that. But certainly one of them is that he spent his undergrad years getting both a degree in math and a degree in engineering. The irony, and I should say this, the irony is he ends up at times in his career getting criticized by mathematicians for not being mathematical enough and getting criticized by engineers for being too mathematical. And so there is this sort of irony that, like, as revered a figure as he is, in his day, he does endure just a little bit of criticism from certain quarters for not being completely of one field or completely of the other. But it never seemed to bother him. And frankly, the work speaks for itself.
You're referring to his thesis, a symbolic analysis of relay and switching circuits, when you're talking about his first big breakthrough publication. Describe the insights that he had in this paper.
And some of the insights are essentially that anything that you can do in Boolean logic, you can actually do with circuits. So let me step back and explain a little bit about what I mean by that. Claude Shannon, as Jamie mentioned, studied Boolean logic when he was an undergrad, and what Boole had done in the 19th century is show that everything that we think of when we think of logic can actually be automated in a sense that you can substitute in some very simple and clear terms and operators, things like and, or, not, if, and so on, things that your listeners might be a little familiar with. But the interesting thing is that Shannon showed that whereas Boole had boiled down logic to this essence of symbols and operators, you could actually use the electrical switches in early computers to act as these symbols and operators. So for instance, if you wanted to represent X and Y, you would have a current flow through two switches in series so that they both had to light up, for instance. Or if you wanted to represent an if, you might say if the current flow through X number of switches, then a light will light up on the other end. But anyway, what Shannon basically showed is Chris Dixon, who wrote a great piece about this in The Atlantic, put it, Shannon really showed how to map the rules of logic onto the physical world, basically how the physical components of computers can do everything that we can do when we do logic. And this meant on a really simple level that computers could begin to be thought of in a sense as almost artificial brains. Not as if anything was advanced at that point yet. When Claude Shannon was coming up with basic circuit design, he was showing things like how you could make a circuit design for a basic combination lock or a circuit design for a sound system or so on. But what Shannon was getting at was this idea that we can hardwire logic directly into our thinking machines. And at the same time, he was also showing that circuit design, because it can be boiled down to this symbolic logic, is no longer something that has to be trial and error anymore. It's something that you can do strictly on paper, strictly in an abstract way, and then you can map it onto your system rather than getting in there and getting your hands dirty before you know what you're trying to do. So in a sense, what Shannon does when he writes his paper is lays the groundwork for digital computers. Up to that point, as we discussed in the book, there had been analog computers. There had been computers that, in a sense, performed analogies with the equations they were trying to describe, and were remarkable machines in their own right. But what Shannon showed is that digital computers, which are computers that use, on-off systems, whether they're in vacuum tubes or in switches or relays or later on in transistors, that these sorts of digital systems or binary systems can be much more efficient and have a much wider range of capabilities. And the interesting thing is that Shannon is working on this paper right when Alan Turing is working on his similarly important paper on the concept of what goes on to be called the Turing machine. Even though they're not really aware of each other's work at this point, simultaneously they're both, what Walter Isaacson calls the sort of annus mirabilis of modern computing. They're both laying the groundwork that all of our computers now stand on.
That insight that he had in a symbolic analysis of relay and switching circuits in his thesis, was it instantly recognized by the scientific community as being as important as it eventually turned out to be?
In one way, yes, which is he's given the unfortunately named Nobel Prize, and the reason you have to say unfortunately named is because it's not quite as impressive as the Nobel Prize. It's an award given to a promising young engineer for a specific piece of work. It is a very prestigious prize for a young engineer. It ends up giving him a little write-up in the New York Times. He's asked to give a speech in Washington, D.C. And remember, he's 21 years old, and he's speaking to some of America's great engineers about this paper that he has written. And so it does mark him out as someone with a lot of promise and potential. But you have to remember, computers at the time were room-sized machines. They were all analog. And so it wasn't as though someone could take his paper and immediately put anything into practice. It merely provided engineers with a set of useful shortcuts. Now, it's still quite the conceptual leap to create those shortcuts, but he did get a bit of recognition. I don't think that the world would fully understand what the paper meant really until, the 2000s and into our time.
So who were the other contemporaries that worked with Claude Shannon throughout his earlier career, and how did they build on his work?
Well, we talked especially in the book about Claude Shannon's most important early mentor, who was someone by the name of Vannevar Bush, who at that time was a professor and a vice president at MIT. And the way he came into contact with Shannon was that he hired Shannon as both a graduate student and as an assistant who worked on Bush's early computer, the differential analyzer, which was one of these enormous analog computers that I mentioned. And it's through doing that work that Shannon lays the groundwork for the next stage of digital computing. But at the same time, Bush wasn't just someone who mentored Shannon. He was one of the great scientific networkers and organizers of the 20th century. I think a major national magazine called him the General of Science. That's a little bit later on when he's part of organizing the scientific war effort. But that just gives some sense of the testament to Bush's influence in the mid-20th century. He actually goes on to become the first presidential science advisor. He has a tremendous eye for talent, and he sees in Shannon someone who isn't just skilled at designing circuits and at doing math, but really is someone who could turn his genius in really whatever direction he wanted to. So Bush does a couple of things. One, he encourages Shannon, in a sense, to get out of his comfort zone. He encourages Shannon to take on projects that he might not have even considered. So after Shannon writes his famous master's thesis, Bush tells him, well, why don't you go write your dissertation on theoretical genetics, which Shannon had never been exposed to, a subject matter that he knew very little about, but he goes and he learns the field, he learns the basics, and in this dissertation, which is an algebra for theoretical genetics, Shannon invents an entirely new notation that can help express the gene frequencies in entire populations of organisms and how they interact. He decides not to publish it, even though Bush and other people in the circle said that this was publishable quality work. Shannon just doesn't really stay interested in it because he imagines himself as more of an engineer, applied mathematician type. And people said after the fact, James Crowe, a geneticist who reviewed this paper many decades after the fact when Shannon was a household name, and he says it's a pity Shannon didn't go ahead and publish it because it actually would have advanced the field by a number of years. People didn't get to Shannon's insights until quite some time later. So, in any case, Bush is an important early mentor in Shannon's life. We could also mention Barbara Stoddard Burks, who worked with Shannon, giving him sort of a crash course in genetics that helps him to produce that dissertation. And then later on, when on the back of all this impressive work, he earns a fellowship at the Institute for Advanced Study in Princeton, that's when he comes into contact with some of the most remarkable math minds of the 20th century. So Shannon, at that point, crosses paths with people like John von Neumann, Hermann Weyl, and, of course, Albert Einstein. And he's never especially close to any of these people, at that time at least. But it still, he describes it as something of a formative experience, at least, to be in the same vicinity as Einstein. And there's actually a great story when Einstein comes into one of Shannon's lectures at the IAS in Princeton. So Shannon's up at the front of the room talking. Einstein walks in the back. He sits down in the back row, listens for a few minutes, and then leans over to someone and whispers in the guy's ear, and then heads out again. And Shannon, immediately when he's done, he rushes up to the back row to find out what Einstein had thought about his lecture. He said, "What did Einstein say?" The guy said, "Well, he just wanted to know directions to the men's room." So, sadly, there wasn't as much overlap between, the likes of Shannon and Einstein, Shannon and von Neumann, Shannon and Weyl at that period as we might have liked. But it does give us a sense that Shannon was already starting to move in these relatively elite circles. Of course, the next major step in his career is that he goes on to Bell Labs, and we can talk a little bit more about that. But the great thing about Bell Labs as an incubator for Shannon's genius is that it's the sort of place that had no qualms about investing in basic research, the sort of place that had no qualms about setting people to work on projects that might not pay off for decades, which is the case of Shannon's information theory. And of course, before we could get to that, there's a lot of work Shannon has to do in wartime, but we can get into that a little bit later if you'd like.
Grammatech Code Sonar helps development teams improve code quality with static analysis. It helps flag issues early in the development process, allowing developers to release better code faster. Code Sonar can easily be integrated into any development process. Code Sonar performs advanced static analysis of C, C++, Java, and even raw binary code. Code Sonar performs unique data flow and symbolic execution analysis to aggressively scan for problems in your code. Just like battleships use sonar to detect objects deep underwater, engineers use Code Sonar to detect subtle problems deep within their code. Go to go.grammatech.com/sedaily to get your free 30-day trial exclusively for Software Engineering Daily listeners. Code Sonar analyzes your code and it delivers a detailed report. The Code Sonar user interface provides all the information that you need to quickly understand the reports, follow cross-functional paths, understand cross-references, quickly navigate between files, and visualize large pieces of your code. Go to go.grammatech.com/sedaily to get your 30-day free trial and unleash the power of advanced static analysis. Thanks to Grammatech for being a sponsor of Software Engineering Daily. Well, yeah, I did want to go into the coincision of World War II and Claude Shannon's joining Bell Labs, because I think that's a really interesting moment in history. But let's just step back and talk real quick. I know you guys weren't really writing about this, but Bell Labs, I keep hearing interesting things about the history of Bell Labs. I'm not much of a historian myself, so when I read something like A Mind at Play and I have a taste of history and I look at Bell Labs, I'm like, wow, this looks like something like Google looks today or like Facebook looks today, where you have a company that it has such a great profit center that they can afford to think 10 or 20 or 50 years into the future and start to invest in those technologies. So what was going on at Bell Labs, let's say, near the beginning of World War II? And also, I'd love to know if you have any historical context on this, what happened to Bell Labs? Why is Bell Labs not a Google today?
Yeah, it's an extraordinary organization, and we were actually introduced to Claude Shannon because of a book called The Idea Factory, which is a narrative history of Bell Labs during the 20th century, written by John Gertner. John was also an incredibly generous collaborator in helping us tell Shannon's life story and encourage us from the get-go, so he definitely deserves a shout-out. But it's a great book, and you see this organization that in the span of less than a century, you can just sort of list off what they invented. The fax machine, partial invention credit for the laser. They invent long-distance phone calls. They invent long-distance television transmissions. Movies and sounds, the sounds and images in movies weren't synchronized. Bell Labs figured out how to synchronize them. And that's all on top of course, inventing the transistor, which is the foundation for all modern electronic devices, and winning 6 Nobel Prizes, and playing host to someone like Claude Shannon, who develops information theory. So it's this extraordinary place. And there are a number of things that we think that made it what it was. One is the obvious one. They had essentially a government-backed monopoly, so they had kind of endless resources so that they were able to think decades into the future, right? They ran the phone company, or they were the phone company, and they had quasi-monopoly on that. And so they had vast resources. But what they did was invest those resources in a variety of different directions, one of which was building out this mathematical research group, of which Claude Shannon was a part. And it's really interesting because the guy who kind of created this was a man named Thornton Fry. And Thornton Fry was this sort of Midwestern, kind of very buttoned up, sort of stiff guy who realizes that a lot of academics are going into academic math departments and they emerge not wanting to stay academics, but they don't quite know what to do because their training hasn't really left them equipped to do, engineering. But he knows that these people are intelligent and smart, and he himself has a PhD in math, and he understands the value. So he builds a team of misfits, basically, and hires all of these kind of mathematicians like Claude Shannon to come in and essentially pick their projects and sort of be roving consultants for the phone company. Only a company like Bell Labs could have done that. It was a prestige lab that's it was one of the most prestigious labs in the United States, which still managed to leave room for that kind of experimentation. And it gave its researchers the ability to think decades down the road, to ask yourself there was a great quote from somebody we interviewed he said something like, we were encouraged to think decades down the road because we figured we would be there decades down the road. And so if something we worked on didn't apply until then, totally fine, we'll be around. And so they had this kind of confidence and self-assurance. One of the other things they did that's really important, at least in Shannon's story, is they published. And so it's common for us to think about companies having newsletters or having blogs. Bell Laboratories published a full academic journal for most of the 20th century. It was called the Bell System Technical Journal, and it's where Claude Shannon's paper makes its first appearance. But if you just take a step back, this was a private sector company. They had no reason to be publishing an academic journal, but they had so many PhDs who didn't just want to necessarily contribute to the work of their company. They wanted to publish. They wanted to get recognition. They wanted to win Nobel Prizes. And so they had this academic journal where people were publishing, and they made its way around the country. It got picked up in university departments, and it was very widely read. And so it's this really unique, sort of like a think and do tank, because they obviously had a responsibility, which is the upkeep, maintenance, speed, and quality of the phone system. But they're also inviting all these people in who are doing all kinds of crazy stuff. And so it's a really, really unique place. I think it's tough to find a company today that matches what they're doing. I mean, I think there are bits and pieces in Amazon. I think just in terms of scale, I think Google's doing some interesting things. Facebook has, I think, adopted in many ways the kind of experimentation, the quality of constantly trying new things that Bell Labs had. And I will say Mark Zuckerberg actually did recommend a book on Bell Labs as part of his sort of yearly book club or whatever he was doing. And I think it was a sort of not so subtle signal that he was trying to make Facebook into the next Bell Labs. It's an extraordinary place, and it really is one of it's one of the most important aspects of Claude Shannon's life that he ends up there. And he does end up there, as you mentioned, because of the war. And like a lot of private sector laboratories, World War II for Bell Laboratories means government contracts to do a variety of things that help the war effort. Bell Labs is working on things like fire control. How do you shoot down moving objects in the sky from a Navy destroyer? They're working on things like cryptography, not just the breaking of codes, but also the creation of codes. How do you encrypt messages across the Atlantic so that they're secure? So all of these things are being paid for by the government. They're being implemented by Bell Laboratories and worked on by Bell Laboratories. And into that mix steps, a fresh PhD Claude Shannon.
Right. And what compelled Claude Shannon to join Bell Labs during World War II?
Well, it's a few things in our view. One is that he simply was not excited about being drafted. He said in some of his letters and some of his interviews later on after the fact, I'm not an especially physically strong man. He's in fine health, but on the other hand, he didn't really fancy himself shooting people with a gun. He also thought that he could really contribute in a much more high leverage way by putting his brain at the service of the war effort. And this was, of course, in line with what a lot of the top mathematical minds of the U.S. were doing at the time. They were working on all of the mathematical aspects, some of the things that Jimmy mentioned, of organizing a tremendous war effort. And this wasn't just the Manhattan Project, which I'm sure we all know about, or even just the perhaps the Bletchley Park project and the Enigma project that Alan Turing was part of in the UK. There were also projects and things like fire control, which Jimmy talked about, which wasn't just an engineering problem, it was a statistics problem about how do you estimate or make inferences about the position of a jet fighter you're trying to shoot down when it's moving at extraordinarily high speeds. But in any case, that's part of the motivation for Shannon. The other part of the motivation is that in this time, in the early 1940s, he's not going through an especially happy period in his life. His first marriage has just ended. He's at a bit of a professional standstill in that he's not sure where he's going to take his skills and go next. So when this offer comes to Shannon from some of his contacts, it really improves his life in a number of ways. One, it allows him to contribute to the war effort without actually enlisting in the army. And two, it gives him direction. It gives him some projects to work on and some really constructive ways to put his math brain to use. But three, one of the things that's great about the culture of Bell Labs that Shannon especially takes advantage of a little bit after the fact, after the war winds down, is that, as we've said, it allows tremendous leeway to people like him, especially in the mathematics group organized by Thornton Fry, that Shannon would take full advantage of. There's this project on information theory. In some of the papers that we found of Shannon's in the Library of Congress, and we saw evidence that he had been noodling this, that he'd been going back and forth on the concepts for almost a decade. Some of his early letters at the IAS in the late 30s, early 40s suggest he was starting to think about the mathematical properties that all sorts of messages have in common, whether they're telephone or television or telegraph or so on. So he was interested in this question from a very early point in his career, in his early to mid-20s. But of course, it's not until 1948, when he's 32, that the paper actually comes out. For a long time, he sort of incubates it as a side project, as something that he does on nights and weekends on his own time when the Bell Labs wartime work isn't especially interesting to him that day. But also the great thing about being at Bell Labs is that once this becomes sort of his full-time job, he's able to bring it to completion, because once the war effort has wound down, no one's really pressuring him to do something that's going to have an immediate commercial payoff. And of course, the fascinating thing about what Shannon does in information theory is that although it has a really important intellectual payoff, people wouldn't really start to see the fruits of what Shannon predicted for several decades after the fact. But I think it was to Bell Labs' credit that they created an environment in which work like this could be produced.
I think it's worth pointing out that, we talk about the wartime, or at least military technology often creates a foment for practical consumer technology. Like it evolves from military technology over the course of 10 to 20 years to consumer technology. I mean, we've seen this with the internet. I'm sure there's other examples. And I think this happened at Bell Labs with the work on cryptography. Claude Shannon was working on cryptography, and during the war, kind of the only clear applications of cryptography was like, as far, you guys can correct me if I'm wrong, is let's figure out how to hide our messages from other people, and perhaps figure out how to decode the messages of our enemies. But this work, in Claude's playful mind, unlocked his mental capacity to think about some broader applications to the considerations he made in his cryptographic research. Why don't you talk about the importance of his cryptographic research, the impact he had on the field of cryptography, and how that progressed to the set of ideas around data and signal processing that became information theory?
Yeah, so Claude Shannon had this great quote about it. He said that it was one great flow of ideas from one back to the other. And that's certainly true. He's actually working on these things concurrently. Right when the war ends, he publishes a paper that's a theory of cryptography that establishes some of the conditions for to prove the unbreakability of a certain kind of code called the one-pad code, the one-time pad code, which is really difficult to actually produce in actual wartime circumstances. But Shannon showed this theoretically unstoppable. In any case, one of the ways in which cryptography filters through Shannon's playful mind and through his pre-existing interest in codes of all sorts and gets to information theory has to do with the basic principle behind the way that code breaking works. And code breaking works because humans, when we communicate with one another, we're fundamentally predictable. Language is understandable within language communities because it obeys all sorts of implicit rules. And these can be rules like spelling, they can be rules like grammar, they can be rules of what's topical in a sentence, and so on and so forth. And people who work in the field of code breaking, like Shannon did, had come up with all sorts of sophisticated techniques to use these predictabilities in language to break and decipher codes. To a certain extent, code breaking will always remain possible because language, in order to be language, will always remain within these bounds of predictability. But anyway, the way that Shannon ports these insights over to the realm of information theory is to bring this concept of predictability and uncertainty into the meaning of information. One of his major insights, because there are several in the 1948 paper, A Mathematical Theory of Communication, is this idea that information is something that resolves uncertainty. In other words, the more surprising it is that a symbol is chosen from a set of symbols, the more information is contained in that choice. So the basic example Shannon gives of this is the idea of flipping a coin. If a coin is heads and tails and it's fairly weighted, it carries, Shannon said, 1 bit of information. In other words, it stores one equal choice between two different positions. But if the coin becomes less uncertain, that is, if it becomes weighted so that it, say, lands heads 75% of the time, the coin itself becomes a less robust storage device. It starts to store less than fully 1 bit of information. And Shannon showed how you can actually calculate the amount of bits in storage devices like this. Then there's a nice parabolic graph in his 1948 paper where he shows that as the coin becomes 100% weighted to heads and 100% weighted to tails, the information content of the coin is 0 because it doesn't surprise us. But the parabola reaches its height right in the middle at that point in which it's actually a 50-50 chance. So anyway, that's the basic situation of information, and we can get much more complex from that. But what this leads to, this fact that humans are predictable when we communicate, is the idea that much of our messages that we send to one another are also, they also have redundancies in them. That is, there are lots of parts of our messages that don't carry semantic content. There's lots of bits that don't really need to be there, in the sense of because what we say is predictable, there's a lot that doesn't really get the point across and is just sort of in there for filling. Just a very basic example. In the English language, when you use the letter Q, you're almost guaranteed that the next letter you're going to see is going to be the letter U. And what that means is that a lot of times the letter U is redundant. It doesn't really tell us anything new about what that word is going to be, and it can usually be safely cut from the sentence. Shannon gave a great example of this. He just wrote a sentence by taking out all the vowels, which looked like most people have little difficulty this sentence, which is just a compressed version of most people have a little difficulty reading the sentence. It works a little better if you type it out than if you say it. But anyway, what Shannon's theorems in the information theory paper are essentially about using these redundancies and predictabilities in language to strip out all the excess and all the fat, which is the process of compression, and 2, to figure out ways of adding back in redundancy to act as a sort of shield against noise and errors and distortion, which really enables us to send messages with complete accuracy, or in Shannon's slightly more accurate terms, with an arbitrarily small amount of error, or a rate of error as small as we would like. And this last result, that essentially flawless communication is possible at any distance, no matter what the message or the medium, was the most surprising result of the paper. People were stunned that Shannon had proved that codes like this to allow flawless transmission of information must exist. And the way it connects back to code breaking is that he had begun to think rigorously about what you can do with predictabilities and redundancies in language many years previously. And although he'd been interested in communication for some time, we think that it was this immersion in these fundamental cryptographic questions that sort of acted as the key that unlocked one of these major insights.
Who do you use for log management? I want to tell you about Scalar, the first purpose-built log management tool on the market. Most tools on the market utilize text indexing search, and this is great for indexing a book, for example. But if you want to search logs at scale, fast, it breaks down. Scalar built their own database from scratch, and the system is fast. Most of the searches take less than a second. In fact, 99% of the queries execute in less than a second. That's why companies like OkCupid and Giphy and Career Builder use Scalar to build their log management systems. You can try it today, free, for 90 days if you go to the promo URL, which is softwareengineeringdaily.com/scalar. SCALYR. That's softwareengineeringdaily.com/scalar. Scalar was built by one of the founders of Writely, which is the company that became Google Docs. And if you know anything about Google Docs history, it was quite transformational when the product came out. This was a consumer-grade UI product that solved many distributed systems problems and had great scalability, which is why it turned into Google Docs. And so the founder of Riley is now turning his focus to log management. And it has the consumer-grade UI. It has the scalability that you would expect from somebody who built Google Docs. And you can use Scalar to monitor key metrics. You can use it to trigger alerts. It's got integration with PagerDuty. And it's really easy to use. It's really lightning fast. And you can get a free 90-day trial by signing up at softwareengineeringdaily.com/SCALYR. softwareengineeringdaily.com/scalar. And I really recommend trying it out. I've heard from multiple companies on the show that they use Scalar, and it's been a real differentiator for them. So check out Scalar, and thanks to Scalar for being a new sponsor of Software Engineering Daily. Yeah, when I was in college, I took a class where we did some work with some of the algorithms that Claude Shannon had developed, and it was really mind-blowing just to write this out on paper and to understand the degree to which you can compress information using some of the insights that he had. I think you gave a good explanation for them, but people who want to see this firsthand, just look up some of the, I guess, theorems or algorithms that have been built up around his work. Can you talk about what applications what were the applications for this encoding work at the time? I mean, I guess I don't know much about what the technological mediums were like back then. I have a pretty limited understanding of how technology works below the highest levels of software. So, if you can let's say you can take a sentence and let's say you're going to take a sentence and you want to encode it in binary. And then you encode it in binary, and then you want to condense it. You can condense it down using some of Claude Shannon's work on information theory. Okay, there's certain redundancies in a word, especially after you convert it to binary. What are the signals? I mean, is this just information that is being passed over telephone lines, or what exactly was the advantage of compressing information in the 1950s?
Well, a couple of things. One is the interesting fact in Shannon's paper that it's not just telephone lines. As one of the information theorists we spoke to in the book said, that Shannon really showed that bits are the universal interface. They work for television, they work for telephone, they work for video, they work for text. It doesn't matter what medium you're using. As far as the payoff of Shannon's work, it doesn't really kick in for quite some time. We think actually one of the earliest applications of a code inspired by Shannon, because these codes that I mentioned for digital encoding of messages, Shannon showed that they must exist, but he didn't actually provide them, which gave engineers a lot to work on in the intervening decades. So the first one that we know of was actually launched with the Voyager 1 space probe in the late 70s. So to show the power of these codes, the Voyager 1 spacecraft goes out to the very edge of the solar system, and by 1990, it's 4 billion miles away from Earth. It turns around and it snaps that famous photo of the Earth that Carl Sagan calls showing the Earth as less than the size of a pixel. He calls it a mote of dust suspended in a sunbeam. It is very poetic Carl Sagan-y kind of terminology. But anyway, the coding that allowed NASA to take that photo and then compress it and protect it from error and send it across 4 billion miles were the kinds of coding predicted and demonstrated in a rudimentary form in Shannon's paper. So when you ask about what this coding actually implies, we get into a little bit in the book. Of course, we get into it on a basic, on a layperson's level, which means that we're not showing you how to write these codes, but we're using some basic examples that Shannon used for lay audiences to explain what exactly this meant. So one basic example he uses, and he actually does this when he writes an Encyclopedia Britannica article about what information theory is in the mid-50s. He goes on and says, well, imagine that you have a language with 4 letters, A, B, C, and D, and you want to come up with a code to transmit these letters, and you know that some letters are more common than others. Like you say, in your language, the letter A has a frequency of 50%, the letter B has a frequency of 25%, and so on. So it's a little bit like English in that some letters happen more often than other letters. And he says you can be lazy about this, and you can use the simplest code possible, or the most intuitive code possible, where each letter gets 2 bits. So A is 00, B is 01, and so on and so forth. But it turns out, if you know that some letters are more common than others, you can assign the most common letters fewer bits, and you can assign the less common letters more bits, so that you're actually saving bits on the letters that you're using most often. And if you do this, Shannon shows that the optimal code in this really basic 4-letter language actually gets you from 2 bits per letter to 1.75 bits per letter, which doesn't sound like a lot, but over over real-world actual messages is enormous savings. And although this is a really simple example that just has 4 letters and a couple of trial codes, this basic process of using the fewest number of bits for the most common symbols or most common images or so on is the foundation of what Shannon shows how we can use redundancies and predictabilities to do things like compression. And again, Shannon doesn't exactly develop these codes in the immediate aftermath of the paper, although he starts work on them and his students further after him start work on them. But he does point people in a remarkably productive direction, and people are actually still developing the sorts of codes that Shannon proved the existence of to this day. It's still a really fertile area of research.
Claude Shannon eventually leaves Bell Labs. He returns to MIT. Why don't you, I guess, abridge the conclusion of Claude's career, and then I'd like to talk about the present and maybe the writing of this book. But why don't you just kind of wrap up what Claude Shannon did between leaving Bell Laboratory and, I guess, the end of his life?
So it's a fairly long period, and he manages to do a lot. Now, the tricky thing is there's sort of 2 schools of thought on this. One school of thought is best articulated by Richard Hamming, who in a famous paper called You and Your Research, which I imagine a lot of your listeners have come across at some time or another, but if not, they should check it out. He sort of dings Claude Shannon. He says that after 1948, and then a little later in the late 50s when he moves to MIT, Claude Shannon kind of hangs it up. He sort of walks away, and he doesn't have anything there isn't any future work that approaches the level of rigor and thoughtfulness as the 1948 paper. And there's some truth to that, but it's sort of an unfair fight. I mean, you're comparing the rest of his career to this landmark paper that developed an entire field and led to so much. We tend to take a different view of Claude Shannon's later life, which is his curiosity did what it often did. It moved to other things. So Claude Shannon becomes one of the earliest thinkers, writers, speakers on artificial intelligence. He also builds technologies that anticipate a lot of our modern artificially intelligent technologies. So he builds a mouse that can solve a maze and then remember its path back through the maze, which doesn't sound that impressive to a world of self-driving cars, except that Shannon's doing this in 1956, and the mouse is a huge, huge hit. So he ends up in Time magazine with a headline that says, this mouse is smarter than you are. He ends up in the pages of Life magazine. He gets a spread in Vogue. And all of this is because he's saying things like, I think there are going to be robots that walk on the moon. I think that there are going to be robot housekeepers. I think that robots are going to be more efficient than humans at many, many things. And I think we should embrace this future and bring it to pass as quickly as possible. So he's doing a lot of that kind of work. He's also dabbling in some of his personal hobbies, juggling, unicycling. He writes the world's first paper on juggling. He kind of articulates a theorem for juggling. It's a long paper, too, so it's not an inconsequential paper, even though to some people who were his contemporaries, they were thinking to themselves, well, this is the great information theorist. What is he doing? He's writing papers about juggling. To be honest, Claude Shannon didn't care. He had established his reputation. He had 2 named professorships at MIT, and he was able to pursue his own private curiosities. He builds a 2-story, it was called a toy room. They didn't particularly like that name, but it was essentially a 2-story workshop that was an addition to his house where he could go and play. He builds, along with Ed Thorpe, a wearable computer, one of arguably the world's first, if not the first, and they use it to go to Las Vegas and they get a slight advantage at the roulette tables. So he's building, experimenting. Sadly, in the late 1980s and early 90s, he's diagnosed with Alzheimer's. And, we describe this as sort of one of the great cruelties of Claude Shannon's life, that so incredible a mind that it was a disease of the mind that ultimately led to his death. And so he's put in a nursing home in the mid-90s, passes away in 2001. And, in a way, the other sort of unfortunate thing that happens is that Claude Shannon is largely forgotten. Within his field, he's a giant. I think a lot of your listeners are going to be familiar with him. But if you went to the average man on the street and, said Albert Einstein, they would react. They'd have a reaction. They'd have recognition. If you said Claude Shannon, it's unlikely they would know who he is. And so that's another part of his sort of afterlife that he's anonymous. Now, in a way, he probably preferred that. He didn't go chasing fame. Even when fame came to him, he was always a little reluctant. Eventually, he just sort of stops responding to people who are after him and after his time and interviews. But that's kind of how he spends the remaining decades of his life. It is I would say it's like a joyful period. He has a great marriage, children. He has the resources and the time to explore the things he'd like. He becomes interested in, chess playing devices, and he travels the world giving speeches, and he becomes interested in stock picking and does some work there. And so there's a way in which, yes, the latter part of his life, did he do information theory round 2? No. But I think given his paper in 1937, again, the most famous master's thesis of the century, and the paper in 1948 that establishes the field of information theory, I don't know that it's a knock against him that his remaining decades are spent doing things that are more private curiosities.
Why did you two write a book on Claude Shannon?
Well, one of the reasons is that when we read the Idea Factory by John Gardner, Jimmy noticed that Claude Shannon was an important figure in the history of Bell Labs, and that he was someone that we as lay readers had not really come across. But he's one of these people that, perhaps because he wasn't a self-promoter, or perhaps because he was just a quiet personality, hasn't really gotten his historical due. And we were just stunned to think about how many of his accomplishments we are dependent on as sorts of digital natives ourselves. So that's one of the reasons. One of the reasons is that this is someone who deserved to have a full biography written about him that puts his thought and his life and his era into a broader context, and simply didn't have it. And even though this was a little bit outside our comfort zone as people who hadn't really gotten too deeply into the fields of math and engineering and computer science, we thought that Shannon's story needed to be told. And I actually think that as non-specialists and non-experts, we brought something valuable to this project, which was we're trying to explain the importance of Shannon's life and work to people like us, to people who might have humanities backgrounds, or to people that might use computers but not really know very much about what makes them tick. And I think that's really important because it's so easy to take everything in our digital world for granted. It's so easy to just accept these wonderful devices and information storage and means of communication and just think that it's been handed to us on a plate. But I think there's something really almost obligatory in starting to learn about where does this stuff come from? How did it get here? Who made it? What sorts of intellectual work went into making it all possible? And that's part of it. And through this process, even though we're not experts ourselves, we've been able to be guided and mentored in a sense by a lot of people who are experts in the field. They were able to fix our mistakes where we made them. They were able to educate us about the field and about Shannon's time in it and about what made him so important as a thinker. We learned a lot from them. And of course, any mistakes in the book are ours and not theirs. But it helped to know that even though we wrote this book from a non-expert perspective, as people who were interested in Shannon's biography as much as in his math and science, that people who did come out of that background could have some input and could help us explore what makes Shannon so worth knowing and writing about. The other thing is that this is the second book we've co-written together, and we both found that we really do enjoy co-writing books. It really helps to bounce ideas off someone. It helps also to make the workload just seem a little bit more manageable, especially seeing that we both take writing seriously, but we also have day jobs that aren't being biographers. So being able to balance that with the writing work is really something that makes having a co-author really useful. And that's also been another advantage of it. We enjoyed writing our first book together, and I'm glad the second one has gone so well.
So what I like about Claude Shannon is, again, this mind at play and this idea that by stretching across multiple disciplines and not being afraid to step outside of your comfort zone of whatever category you've become an expert in, you can start to pull in disparate things and make breakthroughs in certain areas because other people just don't look at them the same way. And you look at the modern titans of industry, it's clear that a lot of them have this ability to think in multiple dimensions, in multiple disciplines, and cross-pollinate. Obviously there's Steve Jobs with Pixar and Apple. There's Elon Musk, who his business empire is like intertwined. You think about the synergies between Tesla and SpaceX and his other companies. What are the lessons here? Like, to what degree should people, like, I think a lot of people that are listening to this podcast are building their career and they're figuring out, like, maybe they're going deep in software engineering right now, but they have an entrepreneurial drive. Eventually they want to start a company or build some kind of invention. And from my point of view, like, finding the right mix of going extremely deep on a topic and becoming an expert, a mix between that and stretching across multiple disciplines is a balance that one needs to find in today's technological world, where there's a lot of ideas being explored, and to have an insight, you really need to have some sort of competitive advantage, and perhaps stretching across multiple disciplines is that competitive advantage. What are your thoughts on that? Like, the trade-off between going deep and going wide?
Well, I think these are the exact set of questions that we were thinking as we were writing the book. So it's good to know that it sort of generated that similar spark, because these are questions that Rob and I are thinking through, not just within the context of writing a book, but also just personally thinking about where do we stretch some talents we already have, and where do we kind of flex our muscles in a different domain. I'll offer a couple thoughts, and these aren't definitive. I think you can take from Shannon's life, just like you can take from any life, different lessons. But I would say a couple things. One, we spoke earlier about Vannevar Bush, and the lasting imprint of Vannevar Bush on Claude Shannon is this sense that the days of Ben Franklin and Leonardo da Vinci are not over, that it's possible to be talented at many things, that it's possible to reach and try to be a polymath. And I do think Claude Shannon is one of our great 20th century polymaths, right up there with people like Richard Feynman and Steve Jobs. I think that part of it is in our era, it's really easy to get seduced by specialization. I think, the economy kind of pushes you in that direction. Get really, really good, carve out your niche, fortify it, and then live out your days. It's much harder, I think, to stretch yourself and to say, actually, I'm going to go into a place where I'm completely unfamiliar and see what I can get from it. A great example is Shannon, when he becomes more seriously interested in juggling, he goes and just drops by the MIT juggling club. And now he's a named, tenured, distinguished professor who just shows up at the MIT juggling club, where there are a bunch of kind of grad students hanging out, right? You got to imagine, if I think about putting myself in those shoes, like, I get butterflies thinking about doing that. But for somebody like Claude Shannon, there was nothing of that sort. He was sort of ego-free. He was like, well, this is something I'm interested in. I'm going to go explore it. I do think one of the key takeaways from Claude Shannon's life is, like, don't worry about being an amateur. Claude Shannon was an amateur multiple times in multiple different phases of his life. And it's part of what made him great, because he was able to connect and to combine and to produce things that only an amateur could, that only somebody who came to it with no prior knowledge could. He gives this amazing speech in 1952, we call essentially a meditation on creative thinking. And one of the things he says is there's a reason why people who are green to a problem, who are sort of new to a problem, will often come up with the most interesting insights. It's because they don't have any of the biases built in. So I do think one kind of key lesson is, like, don't worry about being an amateur. The second thing I would say that we took from his life is read very widely. Claude Shannon was a very, an incredible mathematician and engineer, again, right up there with the best of them. But in several of his papers, we found references to poetry, references to jazz, historical references. He had read everything from, Plato to T.S. Eliot. And again, it's so tempting in the era of Netflix to, like, choose Narcos over Plato, and God knows I've succumbed to that, and some of your listeners probably have as well. But there is something about that kind of wide reading that I think ought to be encouraged. And again, it's a sort of obvious point, except that it's not something we all do. It's not something that is obviously a part of our lives. It was a part of Shannon's life. He was very widely read. One of the things that people comment on is the impressiveness of the library in his home, that there were just floor-to-ceiling books of all different kinds. And it wasn't all math, and it wasn't all engineering. Part of this, again, is Vannevar Bush. He's also friends with a man named Warren Weaver, and Warren Weaver becomes one of Claude Shannon's great popularizers. Warren Weaver's hobby is he's an expert on Alice in Wonderland, and he has translations of Alice in Wonderland. He has hundreds of translations of Alice in Wonderland, ends up writing a book about translations of Alice in Wonderland. And he, in a speech, encourages mathematicians. He says to a group of mathematicians, I hope none of you goes a week without reading a good poem. I hope none of you goes a week without listening to a good song. And so I do think there's a kind of polymathism that we don't champion enough. And I think Shannon's a great model and exemplar of that. And the final thing I would say is, like, it helps to be, if you're a polymath, it makes you more interesting. It makes you vastly more interesting to people. We joke that Claude Shannon's like a cross between Albert Einstein and the Dos Equis guy, that he could totally make a case for being the most interesting man in the world. And a big part of that is because he just becomes interested in so many different things. He's able to interface with so many different kinds of people. Chess players and card sharks and stock pickers and jugglers and unicyclists all have something to find interesting about Claude Shannon. And so, I think maybe those are the few other lessons. I would say the other one, and we wrote a bit about this in a piece that kind of had its moment in the Viral Sun. Claude Shannon was very disciplined about who his friends were. I'm not sure that it's something that people immediately think about when they read biographies, because you're looking for the subject, not the person who's around the people who are around the subject. But Claude Shannon's friends were all pretty brilliant. He becomes friends with Alan Turing, John Pierce, Barney Oliver. These are all kind of the leading lights in information technology, and many of them had a lot of IQ points to spare. And there's a reason why Shannon's friends with them. They're not sitting around talking about the weather. They are talking about AI, and they're talking about whether machines can be made to think and to do what humans do. And so one of the lessons I think Rob and I took from it is, you really got to be careful who your friends are, because your friends are going to have this sort of impact on you. And in Shannon's case, his friends challenged him. They gave him things to read that he hadn't read before. They all co-wrote papers together. And more than anything, I think they just had a level of conversation and discussion and camaraderie that is probably the envy of a lot of people listening. So those are some of the takeaways. And granted, people are going to have their own, but those are the ones that stood out to us.
All right. Well, guys, it's been great talking to you. I have enjoyed this foray into history, and I can see the line that draws from Claude Shannon to our modern world, and I appreciate you helping me to see the delineation of that line.
Well, thank you so much. It's really been a pleasure to talk with you.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/sedaily. That's symphono.com/sedaily. Thanks to Symphono for being a sponsor of Software Engineering Daily for almost a year now. Your continued support allows us to deliver content to the listeners on a regular basis.
Wow!